example here. But when they talk about forced oscillation, what they're talking about, right? You remember what simple harmonic motion is, right? Who's that?
So it's a idea.
Right? Simple harmonic motion is what?
Simple motion.
Simple motion, right? Okay. Yeah. What is all here?
Now object of body oscillates about a fixed point. Its acceleration is proportional to its displacement from the fixed point, and the acceleration is always direct.
Okay, so right, 30% up it. Nice. And normally in a free oscillation, there is no loss of energy, right? So it will continue to oscillate at the same amplitude. What has happened when you include damping? The amplitude starts to decrease, right? Nice. And you remember what we said, if something has damping, right, and it's losing the energy and oscillating at a smaller value, how do we increase that amplitude now? Madam, how we can do? So it's damped and it's losing energy. What we can do?
Till dry.
It'll dry it. Add energy, right? So we're gonna take a look at how. Let's see if we can take a look at this oscillation here where. Yeah. Let's see if there's anything, otherwise we will have to go to the button that you have put on it.
Because I don't
All right, so let's look at this forced oscillation concept, right? So we said that if something, right, if something needs energy, just go, Michaela. Yeah, if something is losing energy, what we need to do? Add energy, right? So here we have a nice little simulation of how this can work, right? Take a read there.
Everybody gets that. Because they can't
Right, sorry. So I want to show you this concept of resonance. It's something that we experience almost every day. Yeah? So what you say? So imagine sitting on a swing at a playground with nobody around to give you a push and up. Right? To get yourself in a larger, so think of that situation. So you're on a swing, the person get pushed and he leave you. What will happen after a while if you don't push yourself? Right? You're coming back to equilibrium, right? To get yourself into a larger swing, you swing your legs back and forth. Of course, you can't just swing them randomly back and forth. You need to swing them back and forth one time for each back and forth oscillation. So what it's saying is that you have to kind of do it in time, right? So you can't, if you're going backwards, will you push your body forward? No, push your body in the same direction, right? So basically what has to happen is that the frequency is swing moving up. You have to moving at that same frequency. So your frequency have to be the same as the natural frequency of the spring. When that happens, you'll recognize that you will have a nice big oscillation. That's okay? And that situation, we call it resonance. Huh? Total. But remember, you're moving. Once you're moving, you have momentum, right? But we're talking about the concept of resonance where you apply a force of equal frequency. Right? So let's take a look at this here. When an object like a spring has a particular natural frequency at which it tends to oscillate, it can be made to go into a larger oscillation. Yeah. All right. Okay. Yeah. Right. Sorry. When an object it can be made to go into a larger oscillation by adding in small amounts of energy at just the right time with each oscillation. This can be done by an external force that acts with the same frequency. So that's important. It must be the same frequency, right? A situation that you all do experience this, but long ago, right? When we had radios, for us to hear a station, right? What we have to do is turn a little knob, right? And when the frequency is equal, then we will hear the sound, right? That is basically resonance. Right? We can't hear because the amplitude is not large enough.
So basically, I find it resonance.
Basically, we have to find the frequency and the frequency coming in. And when those two frequencies collide, like 94.1 or 90.1, when those frequencies collide, then we get the up.
So your car is like waves on the station, waves on its.
Now, right? If I'm looking at a particular thing, for me to hear it properly, I have to allow it to oscillate larger. So the frequency I send in have to be the same frequency. When they match up, it will be loud enough for me to hear. Right? But you don't have nothing like that now, right?
Yeah.
What? But it's more digital, so you press can. But it's a similar concept. When the frequency of the car match with the frequency, the amplitude. And then we magnify it by using a radio. Right. This can be done by an external force that acts with the same frequency as the natural. So that's the most important thing for today. Well, for now. That resonance only occurs when both frequencies are matched. This is a very popular example. In this simulation below, three identical masses, all are the same, that 2, 2, 2, all are the same, right? Are attached to three springs with the same spring constant. Each mass spring combination has a certain natural frequency. When the bar to which the masses are attached itself is oscillated, the three masses will start to move slightly. If the frequency of the oscillating bar matches the natural frequency of the vibration of one of the masses, resonance occurs. Here's what it's saying. When this bar here matches the frequency of one of these, you will see the oscillation start to get larger. Right? So we're going to try to observe that here. Right? The particular mass will get into a vibration mode with a larger amplitude. Note, all of the springs have built-in damping that prevents the resonance from getting too large, right? So watch it here. See it moving, so it's moving up and down. What you will notice is that this starts to get a little bit larger. You'll see that?
Yes.
Why is that? Why is that larger? This is larger because the frequency oscillating at is the same frequency that this bar is acting at. Wait a little bit again as the frequency gets a little bit larger. Let me see what will happen when the one's lower down.
Wait, don't knock some.
Huh?
Wait, don't knock some.
You'll see now it's oscillating larger.
Wow. I bring back memories. It's in the max.
No, sir. Hey, I should tell. All right. Right. So what I want you to observe, it's a little bit slow, but what I want you to observe is that not all of them have the same amplitude. Right. There's a point in time when one vibrates much larger than the next, and that only happens when this oscillation is the same as the frequency of the rod is the same as this. We were to find that frequency, we got to.
Say that in calculations in top.
Huh? So that we can figure.
I guess you're
Right, watch it here. Huh?
It's just like normal.
Yeah, like normal frequency stuff. But you have to understand the concept of resonance. So you'll see it there? Right? Let me see if I can get this next one for you. There's a next one called Barton's pendulum. I'm not seeing it there. We check out Barton. Oh gosh, when you have videos. On the online was see.
So then I was 90 minutes video.
Alright, this one here. Wait, where is it? Right, I have a question here, and then we'll see how it goes, right? Dante, what you say? Here we have all these pendulums here, all the pendulums. If they all oscillated, and then we apply the driver pendulum, that's this one here. Which one do you think out of all the pendulums will oscillate the largest? And then what? Smallest one?
Yeah.
Anybody else? Remember what we just learned, huh? They both must have the same frequency. So which one do you think might have the same frequency?
The same frequency with Java.
Yeah. It has to have the same frequency as the pendulum.
So it's one of the fifth one.
Right? The one of equal length.
Sorry.
Right? The one of equal length should have the same pendulum. Tell me why. Why is just length I'm looking at and I'm not looking at mass? We talked about this last week. Anybody, you can add 20 to get it right. We talked about this last week. Why are we only interested in the length? The ones with the same length.
The lengths affect the oscillation. Yeah, so
Close. But we proved this last week too. So we proved this formula, T is equal to 2 pi by the square root of L on G. Right? If the length is the same, period is the same. And if period is the same, frequency is the same. Alright. Right, you can make the examiner figure out where you want to say it. Right, but basically I said, right? So if I release this here, Joseph, what will happen? Yeah, explain it to me. Sorry. Huh? Semantic explanation. Before you go. Why it is this one here will have the largest amplitude? Matching frequencies, okay. You can go now. Alright, hold on. I don't know why. You're seeing a link to the simulation anyway.
No.
Huh? Well, I said it. I don't want to pull that. We'll put it outside, you know, someone expect. Hold on, eh? Just now online, I just want to see online, just tell me if you're seeing this tell me if you're seeing this simulation, I mean this video here. don't know what part of it.
Yeah, life and grace. So the 90 minute video, let's explain it.
Online, Josh, take us.
Yes, sir.
I know I will. Right. Start here.
Welcome back. I've got an interesting and unusual experiment to show you today, and it goes under the title of Barton's pendulums. The equipment looks quite complicated, but in fact it's really simple. All we've got is a wooden frame here, and hanging on this side and across to this side is just a piece of string. It's a sort of washing line on a small scale. And then hanging from that, tied on, is a piece of string with quite a heavy weight on it, and then some paper cones on different length strings. So the important thing is here, we've got a heavy weight hanging off our mini washing line and a series of other objects hanging off it, all of different length. So let me show you what we do with this. The first thing to do is to take the metal weight and just to lift it up and let it oscillate. And you watch the white paper cones. And after a short period of time, it settles down and you get quite a remarkable result. That most of the paper cones don't move very much, but just one of them, here you'll notice it's the one that's second longest, seems to swing up and down much more than all the others. I'll film this from the side so you can see it rather better, but this really is going to take some explaining. Right, I'm going to start it off again and have a look at what happens to the cones as it begins.
What you guys are move you, right? Right, so that's the concept of resonance.
Why is that?
Huh?
Why not? So we're just
Why that could somebody can explain to him why that could move
no, but when people eat you have been you don't know.
then you adjust the length. Right, so if I pull it down, I should
No, it comes up on number.
if that's true, you mean?
Yeah.
Yeah, same pattern. Right? Yeah. Alexis Adam.
No, I just listen.
Alright, let's go back to the notes there. Right, this next part of the class, plenty read it. So Adam, come and start up and read it. Right, so you'll see concept there of resonance, right? Let's run through some of the notes, no writing, just had a listen, not sleep. Fall asleep there, okay? So
Yeah,
right, except for this, most of the things.
That's how to discuss.
Right, so you remember we talked about this, called damping and thing, hold on. Talk about critical damping, now we try to reverse damping, right? Right, force oscillations. Right, so in order to keep it damaged system, sorry. Watch it. In order to keep a damped system in continuous oscillation, a periodic external driving force must be applied to the system to replace the energy lost. Straightforward, right? Oh no, this is not a number, you know? Right, the oscillation is such as, sorry, the oscillation in such a systems are called force oscillation. Yeah, you're forcing it, right? Right, the frequency of the driving force or the driver is called the driving frequency or the forcing frequency, while the frequency of the system is called the natural frequency, right?
Yeah, we combine frequency. And combine. So you just sit down combine.
The amplitude of the force oscillation, right, depends on the relative values of the driving and the natural and the extent to which it's damped. All right. So what we have here is a little graph showing how everything behaves on undamped, lightly damped, heavily damped. Right? So I am going to explain lightly damped.
Like a normal shoes.
Yeah, pretty much. Right? Because it only happens at one frequency. Right? The amplitude is only max at one frequency. That's why it looks like a normal. Right? What you see?
So that's us pretty on down. So that's us simple.
Try to get that line there.
So that's us simple.
Huh?
That's us simple.
What's up?
Pretty on down.
What is it? The line? You can say so.
Is that what much?
No, that one.
That's us simple.
Yeah, you can work out.
Alright.
Right? Yeah. All right, so what's here? Christian following? Looking like a sleeping Christian. You good? Oh, you got 2 minutes on here, that's all right. See what it's fighting now. Right, so what's this here? What this shows here is shows how the amplitude changing with frequency. F naught is the natural frequency of the object. And we know, Nathaniel, that the resonance only going to happen when the natural frequency equals to the force frequency. So it's only going to happen somewhere around here.
So we have a diagram.
Ah, yes, it came on. So we had to plug the graph and then explain it.
Oh,
Right? So watch here. If you look closely, look at the lightly damped. You will notice the natural frequency is here. Right? But look at when the max, look at it here. Look at when resonance occurs. Did it occur at the exact same frequency? No, a little bit smaller. Yeah, I know what I tried like that, right? What you will recognize here is that max amplitude not happening at this frequency. That's because it's damped, right? And the more you damp it, it adjusts the frequency a little bit, right? The more you damp it, right? Because remember, this formula here was designed for what? Something totally undamped, right? So two things you're going to recognize. The more you damp it, the smaller the amplitude. That makes sense, right? If it damp, then your max amplitude wouldn't be the same, right? Lightly damp a little bit higher, you'll see it now. But the only thing that you have to learn is that the frequency happens a little bit earlier. So if the frequency value for F naught is 20, for lightly damp it might happen at 18, and for heavily damp it might happen at 15. Right? The frequency happens a little bit earlier. Right, but I have a little problem here. Look at this undamped. This undamped have no ceiling. Just going. Why? Think about it. Severe, you are expert. Let's you can come up your phone. All right.
It will never equilibrate.
It will never reach. No, equilibrium is coming back to zero. But think of the situation. It's an undamped situation, and you apply a force oscillation. Still be simple, I know. Something happening there. Anybody?
So the
Huh? So the question is, we have a situation where we have a pendulum and it oscillating in an undamped scenario. Right? Undamped. Remember what undamped means, right? And now we apply a force oscillation to it. Why is the graph shaped like this? Why we can't see for all the others, for the blue and the red, we see in max amplitude? Why we can't see it here for the undamped?
Because max exceeding.
Okay, but even if I draw the graph out here, why is it exceeding the graph, Adam?
Because it's so big.
Why then not so big?
Let's say that's not.
No,
And it's a-
amplitude. So energy is for
When we just think about it, what's the point of force oscillation? To overcome what? To overcome damping, right? So if it's not damped, you apply a force there. Right. So if you apply a force, it will end up going to infinity. It'll be real quick, right? You understand why? So this on-down graph stays open, right? Because the value just goes down, right?
On down plus like nature, because it can't
Ah, we're bringing the POD, man.
down plus like I'm like, see more.
They're bringing the POD.
All right.
Yes.
Everybody okay with that?
On down plus like nature.
Right? So just make a note. Did I give it up? Right? So by increasing the dampen, these two things happen. It reduces the value of the maximum amplitude and causes the maximum amplitude to be reached when the driving frequency a little bit less. Just make a note of this. Right? Just get your graph. I know you have it.
Make sure like you don't see the stuff like that.
So the rest, the manager is here push up here for paper was inside you. So the many press run with that.
That's what is going to be.
You teachers being you can run out. You can run out. And I said if he does. Yeah, he doesn't go. But he does. But he's thinking
Right? So that dampen there and what's happened with the increased dampen, right?
So that's our so it's like we go back out.
yeah, you read this is
Look at that, look at that.
you read he shouldn't be less than no, he like skinny as a crap. You don't need to pull on your medicine. No, I see you look at shit stuff when it comes to that. Yeah, not baby. It's not here. Not fashion. You need to remember the secret. I don't go. See, no man, it's like, oh, yeah, that one there, that picture. Oh, yeah, you got it. Oh, that's a job. That's a fire. Oh, I'm watching. Bit like shit.
You're done?
Yeah, can't find videos.
You sure?
Did I send it to you?
Right, so we talk about resonance. Right, we talk about resonance, and then here we have some examples of resonance, right? Some applications, some good and some bad. I got it right, right? Let's go through this quick. So the microwave oven generates a microwave frequency, which is equal to the natural frequency of the oscillations of water molecules. When the food is placed in a microwave oven, the water molecule present in the food resonates and absorb energy from the microwave, causing the food to become hot. Right? Then you have a next example here, magnetic MRIs. Right? The nuclei of the atoms can be made to oscillate by the applications of strong varying radio frequency EM fields, right?
So you say, yeah, starts.
Huh?
Favorite.
Yeah.
And my double sample.
Yeah, that's what MR stands for. When the applied frequency is equal to the resonant frequency of the nuclei, pattern of the energy absorbed is used to create a computer-generated image, which can be used to diagnose of various ailment patients. Right? It has an advantage over the X-ray, right? Because it doesn't use radiation, right? Right? Radio tuning radio wave passing the areal of radio forces the electrons in the areal to vibrate. If the length of the areal is correct for the particular radio frequency passing the area, then the amplitude of the oscillations of the electrons is much larger. A larger signal is then passed to the receiver where the signal is processed. All right? Right, and then you have the dangers of resonance. So for example, this Tacoma's now bridge force oscillation produced by winds and a frequency equal to the natural frequency resulting from the bridge cause it to vibrate too much and then mash up. Right? So the bridge has its own frequency, then wind passing, right? Then wind passing over it had a similar frequency. When they both were the same, the bridge vibrates too much and mash up. Right? Same thing with this, these matchers here. These matchers went across a bridge, and when their frequency was equal to the frequency of the bridge collapsed. Right? Aircraft, same principle. If the frequency of the wings that the wings oscillating at is equal to the frequency of the wind, what will happen? It will vibrate too much, mash up. Right?
So they say in this structure.
Yeah, but so you wings and areas really vibrate.
Rarely vibrate. Yeah.
Yes.
Remember vibration? Do I have to do this? Yeah, vibration is small.
You know, I flap it, he flap
Yeah, yeah, you can go ahead. But how about see that's locked back here. Yeah. For me, no, I got it.
You need to see you wing.
I got it. That's fine.
5.
Bye-bye.
Shit, I don't even know what's supposed to
What? Yeah, I was I am for right? Nice. So that's resonance, right? Next, we're going to go over wave motion. Everything in wave motion is from form 5, right? Except for phase difference.
Seriously, yes, in fact. So Houston,
Right.
say you know something I don't.
Take a little 2 minutes and then we go into wave motion, right?
Oh, great.
Everybody has that. Yeah, so we're asking.
Right, take a little 5 minutes and then we go into wave motion, right?
Sure.
Waves,
There's a flow.
right? Huh? Yeah, yeah. Next month is time, but month. We have class next week, like no one. Yeah. Friday is no class. Another. Right. Next Friday. Skip the start, huh? What is Santa this Friday?
Yeah, Friday.
Where she's having?
I must come. Like it was right, but
Oh. Think about why I answer, yeah. Alright, let's go now, William. Right, so wave motion, right? So we're going back into wave motion, Christian.
Stop booking it for next year.
Huh?
Stop booking it for next year. That's Jason.
Wave motion, right?
Yeah.
Excuse that, I'm gonna have 5 minutes already.
So,
Right? So a wave motion is a means of transfer of energy from one point to another without there being any transfer matter between the points. Right? Waves can be classified as mechanical or electromagnetic. Mechanical waves are produced by a disturbance in a material medium and are transmitted by the particles of a medium oscillating to and fro about their equilibrium position. Mechanical waves therefore require a medium. Okay? They require a medium for which the waves to propagate. For example, water waves, waves on a string, and some waves on spring. Right? They need a medium to pass through, right? Electromagnetic waves on the other hand, Keisha, right? Electromagnetic waves consist of a disturbance in the form of varying magnetic and electric fields. No medium is necessary, however, EM waves travel more easily to a back. Right? All these are examples of the waves, right? Everybody recognize these here? EM spectrum, right? Which one has the smaller wavelength, Adam? Which one has the smaller wavelength? Radio or gamma? Right? Next, we have to know some wave classifications.
that's what I meant.
Right.
That's in order.
Yeah, what from highest to lowest.
This right, Chico. No, right, they call it.
Right? So a non-periodic wave of pulse consists of a single wavefront and is produced by a singular disturbance. A periodic wave produced by a succession of periods of disturbance, which give rise to a wave tree, right? So when you see a like if I keep dipper and the dipper keep hitting the water, it will produce a wave tree. I'm gonna start on page right? Energy movement, right? In unit 1, we're going to focus on stationary waves, something that we didn't do in form 5, right? Right? Energy movement, a progressive wave is one in which there's a transfer of energy from the source to the surroundings, to the places surrounding it. Right? A stationary wave is one in which there's no net transfer of energy, but there's an interchange. So it's like a constant interchange of kinetic potential, but nothing being transmitted. Okay? So we are going to focus a lot on stationary waves. Okay? Right? So like for example, like sound is an example of something that might be experience a stationary wave. Right? So we're going to take a look at these here. Right? Directional displacement for transverse wave, the perpendicular. Remember that? And for a longitudinal wave with what? Parallel. Nice. And you have examples of each. Right? You have examples of transverse and longitudinal. Here we have an example of a slinky producing a what? What type of wave is this? Longitudinal, right? This is longitudinal, right? You have a wavelength between compression and compression, or refraction and refraction. Where they close together is what?
Compression.
And where they far apart is? Refraction, right?
Eso, I don't think compassion. What is it?
No, that's what I mean. Right, graphical representation of waves, right? We know a displacement position. Can I read off period from a graph like this?
If you have find frequency and different.
If you get the speed, right? But from a graph like this, can you read off period? No. But what you can read off? It's a position graph, so you can read off wavelength, right? So what you see? You notice there's no period on this graph. Right? There's no period on this graph, but we know that from here to here is wavelength, or from here to here is wavelength. Far and right. If you have a displacement time graph, then you can read off what? Period and find frequency. Okay?
So,
Displacement position. So it shows how its position changes.
amplitude does not affect pressure.
Amplitude does not affect
Wavelength.
Alright. But it could. But it could.
I have a question.
Yeah. I don't want to say it never, but
And it was like a wire is 4 meters and they bend it like this. And they see the wavelength of that. So that would be 4 meters, right? Before our next wire, that's 4 meters and tiny wave. So wave will go so big.
yeah, because I like the
Right, so then the amplitude would affect wavelength.
the amplitude will vary. When you change, when you also change. It's not one, it's more than one quantity change it. You change period there as well.
Oh,
You change plenty of things. Right? So if you look here, you have period, time for one cycle and press. Just one little mistake you will tend to make. If you see time is ms, what does that mean? Milliseconds, right? Not meters, right? All right, nice.
meters.
So we should know all these definitions: displacement, amplitude, period, and frequency. Right? Everybody okay with that? Frequency is 1 and t, right?
So where do you get hertz from? That was Amali.
Huh?
Hertz.
Yeah, somebody. Right, hertz. Right, hertz is the SI unit for frequency. Right, really important now. Phase difference, right? We only did 2 phases in Form 5, but what were they?
In phase and out.
In phase and out of phase, right? In phase means what?
Yes. So also that's part of
So the crest line against crest.
Right, crest line up, top and top, and they have the same what? They coherent, right? And what outer phase?
So that way it's cancelled.
That's when crest and trough lines up. Right? So you have crest and trough. Okay? Now we're going to go a little more in between. Right? We're going to go in between. We're going to go phase difference could be quarter, half, and so on, right? So what you say? So you want to take a look at Nathan how to find phase difference. Ready? So the phase of a particular point in our oscillation is a measure of the fraction of the oscillation that has been completed with respect to a chosen starting point. All of your phase is between 0 and 2 pi. Right, damn it? So let's take a look at. All right, let's read through this first. The phase difference between 2 particles in a wave is the fraction of the cycle in radians by which one particle leads or lags the other. All right. So let's take a look at this here. This might make sense. I want to show you it, right? Here we have.
So is that sir?
Right, what you say? Phase difference is pi, which is x on lambda by 2 pi. So once you can figure out what x is, you divide it by lambda, multiply by 2 pi, and you get your phase difference. All right, let's start easy. Ignore the one.
So was it first?
I mean, phase difference.
You just want to on the screen or you don't?
So it's
Four.
Huh?
It's okay, what?
X is the distance between, I'm going to show you an example. Lambda. So if I draw two waves like this, you have this red wave here. And you have this blue wave. What is first again? In phase or out of phase? Out of phase, right? So let us see if we can find the distance between here and here. What's that distance there? That's x, right?
Yeah.
How much of a wave is that?
half
Half a wave. So x is half a wave. All over lambda by 2 pi. How long to the lambda? Half of 2 pi is 5. So the phase differences
One.
pi. And pi is how much again? How many degrees? No degrees. Pi is 180 degrees, right? So whenever they say outer phase, they mean a phase difference of pi or 180. Everybody okay with that? Yeah? Right. But okay with that? So that's the way you find size phase difference. Right? Let's take a look at this one here. Any questions online?
So you have.
Huh?
How
much? From here to here, what? From here to here.
Ah.
Half a wave.
Go this one. This one.
No, we reach here yet. Everybody read and blue.
Okay.
I'm not cancel and half of 2 pi is pi, right?
Yes, yes.
Right, this one here, Keshav, how you would find the phase difference to this one here? How you will find the phase difference between the red and the green? You have to measure the length or read off the length, right? Wherever they give you, right? Wherever they give you in meters, it don't matter what centimeters. All you doing is you finding that length and dividing it by the wavelength. Yeah, it will be a graph. But if we had the average, how do I look at it? How much of a wave is that? A little less than a quarter, right? Y'all seen that? A little less than a quarter. Right? Right, question. Which one leading and which one lagging? Between the blue and the green.
Green leader. No, we go the blue leader. No, blue leader. Blue like before. Blue leader.
Are you sure?
Yeah, sure.
What's that? But
Think of who leading.
so, I mean, you short, huh?
So blue leader. Blue leader. Yeah, it starts. Blue and blue. So green market because it come after.
Right?
Blue line.
So if you imagine the axis here of time, right? You remember blue happening before the green. You're seeing that? Blue happening before green. So blue is the leader and green lagging. Right? Right? So blue and green. Everybody okay with that?
Yes, sir.
Alright, nice. So you locate phase difference. So you find the distance between the waves, right? And divided by lambda, multiplied by 2 pi. Right? One paper in the book now. Draw a wave that has a phase difference of pi on 2. Draw two waves, phase difference pi on 2. Let's take a look. Yeah, two waves on the same graph that have a phase difference of pi on 2. I showed you pi. I showed you pi, right?
Yeah. See what I'm getting out there.
Right. A long time.
That's a good place. The kind of good place.
Right? Why not get it?
So that's it.
All right, so watch here. Right, watch this here. So your diagram might look like the one on top. Right? Phase difference of pi on 2 is the same as 90, right? Everybody okay with that? And we seeing that A is ahead of B. Seeing that? A ahead of B.
So, but what if the x-axis is not there?
And then what?
Check position.
It work as well. Right, but it mightn't indicate who happened before. Right?
So if they give position, you can't make any difference on what it
We are, yeah. Right, B ahead of A here, 90 degrees. You're seeing that? You're seeing B ahead of A and then, well, sorry, B ahead of A is second diagram. And look at the third diagram, right? Phase difference is 180. A and B are mirror images of each other. And last one, right? They both what? They're both totally in phase, right? Phase difference is 0. Have you okay with that? And of course, between 0 and 90, you have more, right? Right, you have what? 95, 96. All right, nice. Ah.
So is it the beer? So far. So is it?
What's that?
Reason.
Pablo.
Sí, es el primero.
Galvanized or galvanized. The side. And I still got finish.
It's a bit more relevant.
On the line. Right. Wavelength.
Nice view. I don't like my
Right. Wavelength distance between two successive particles. Speed of a wave. We know speed of a wave, right? Could you prove that formula later? Could you prove B is F lambda? Yeah. All we have to do is this, right? Speed is distance on time. If the distance travel is lambda. How long does it take it to travel lambda?
2. 1 invents it.
How long does it take to travel lambda?
1 and a
1.5. Okay. Period. Right? So to travel one wavelength to T. Right? So if I find 1 on T, I will end up with F. So we get the formula B is F lambda. Alright? Wavefront, a line or surface in the path, of the wave at which all the particles are in phase. Wave, right? Wave perpendicular to the wave showing direction. Right? Some of that's a little bit new. Right? Make a note of this. Intensity of a wave. The intensity of a wave is the right? Is the rate of flow of energy per unit area perpendicular to the direction. So intensity power over area. Anybody ever remember the unit? For intensity, you would have seen it in the air. You'll remember, pay attention to that.
500 pascals.
What?
I was meaning to
Right? The SI unit is watts per meter squared. Right? If you remember doing it in school.
Yeah.
Yeah. A and I, yeah.
And I know what. So I was right. 500 Pascals. No, 5,000 Pascals.
Nothing there with it.
5 Pascals.
Did you want to create a different build?
I think let's take it here. Right? So intensity is power over area, right?
So is E again? So is E? So is E? So work done against it?
Yeah, we're done on time. It's the rate of energy per unit area.
So work done on time by the work.
Yeah.
Wait a minute.
Watts per meter squared. Right, you're going to do this again when we do intensity levels and threshold and pretty here.
So yeah, on the applicant seller, some, yes.
Apply. I just have 100,000.
Go. So you
Oh,
can
mine
check
is-
speed. So you get a previous.
My own name, but outside.
So you can check my speed.
Yeah.
Send it to you. So you
My own
can,
kind of lane, but outside.
so you get a reverse speed.
You know, we don't know how
You know, yes, that would be called 2 weeks, you know.
Give us something to get on now.
Tell them, right, stop. Well, reach.
We just pick
What
the
you want?
topics.
So, Marco, right?
Oh, in school. Yeah, one more check. So,
Right, just pick a topic you like, stop it and charge it.
you
Get some ideas.
what teacher. Apart from the teacher.
We now, we have some of those two.
Yes.
All right,
It will fit up. Blah blah blah. He talk last your sense.
Yes, yes.
right, and last thing, intensity is proportional to amplitude. Right, so like a sound becomes more intense if the amplitude is larger. You all remember in sound waves, we say that loudness has to do with what? Amplitude. So the louder it is, the greater the amplitude. Right? And the louder it is, the greater more intense it is. Right? Last thing you want to look at, I'll give you 5 minutes after.
So which one is the
Polarization.
second flowers? Yeah. Which formula is for which one?
What time is after the?
Right? So circle that in your notes. Intensity is proportional to amplitude squared. We're going to be using that soon.
Say about formula book.
No, for summary, I'll do.
Say about formula book. Wait, say how? Basic is like. Yes, I know formula. Take your thing.
I'll get the next one. But we get the old one. Huh? What? How about that those one?
You can send it.
Huh?
Send it for
Yeah. I'll pay. I'm sitting at Shima Puno with everything from last night. So I decided to like I'm learning about crash course. One get there, second, one time.
So the second one, John.
Why do they? I mean, not I
Send
don't
a message asking them.
Alright, nice, polarization, right? You're going to read that after. Right? What is that there? What is going on there? Some sample out, right?
So yeah, that's it. So what you
I don't have the original, but I'm going to fix it.
What's that? See what? No, wait
Not that again, going. Right? So what's here? Right? What's here, right? So if you look here, these are called polarizers, right? Some of your glasses are what? Polarized, right? And polarizing, what does it do to the intensity of the light? It make it smaller, right? And we just learned that intensity is proportional to what?
Amplitude.
Square.
So technically, what that polarizer doing? Dropping the what?
Amplitude.
That makes sense, right? So let's see what happened here. Here we have a wave oscillating blue and red, right? Right, the red wave disappeared, right? Can the red wave pass through a vertical? No, that's called a polarizer. So it just polarize the wave and make the amplitude smaller.
So anyway, they just decided to jump through.
Can't. Can't.
So
Right? And what would happen if I turn the polarizer perpendicular now to the blue? That pass. So it's totally plane polarized. Right? That's okay? And that's the principle behind the polarizers on your glasses. Huh? Yeah, same principle. But can we polarize a longitudinal wave?
Absolutely not.
Not really, because it just up in one direction, but can we polarize a transverse wave? Yeah, we can. What you're seeing there is a transverse wave, the red and the blue. Okay? So polarization could be used to separate what?
Waves and fields.
Types of waves, right?
Yeah.
Transverse and longitudinal. Ready, son?
Yes, I'm gonna say cancer for
No, but it can differentiate between them. If it can polarize, transverse. If it can't polarize,
they're gonna say experimental software.
yeah. You can do that. Here it's showing you that the amplitude drop. When the light goes in, you see the amplitude smaller. So that means it's less intense and it will protect your eye. Alright? Superposition, you'll remember this. In phase constructive, out of phase disruptive. Alright. Okay, so we're gonna take a look at stationary waves, right? Take a little break and then we're going into that. Alright, take a 10 minutes and then we go into this.
Can I put this?
10 minutes, sir. So let me try and please answer. 10 minutes. Oh, you have that?
Ravi little Teresa is yeah.
Say, can prove this?
Just deal. Yeah.
Science.
Say not to prove that.
I shall low.
One minus.
It's out.
Prove that? There you go.
I know. Second after go. I know none of my answers.
So they don't feel outside. One. So they feel outside.
So I feel like so boring.
Find this boy, you can see everything happening here.
Hey, fun is just hard. Like if I was good at that.
I was so
Yeah.
it's a good building experiment. I know like where you like I think it's on US and or something.
Alright, let's go now, Olio. No, that's more than one round because you're dealing again.
Keep back.
One round. One round, there we go. Alright, there you go.
So take out pussy right now.
I want this.
Sickos of that though. You're solving also.
I'm going to solve this here now. There you go.
You can't solve this.
He can't solve it.
You can't solve it.
Yeah, he can't solve it.
Change pussy. The one on sign.
Alright, let's go.
Done the sign on toss.
Take a front this graph.
Let's sit down now.
If you can solve it. That's it. You front this graph. Send this graph. Send this graph position. Faster though.
Guys, everything shape on the ground.
Huh?
You shape on the ground.
I don't like to.
It's like that.
I'm so. I'm not thinking.
Alright. Watch here. So we're looking at something called stationary waves, right? Right? Just going into this and some calculations and we're done, right? This one of calculation. Right? It combines everything that we learned earlier. Okay? So you remember constructive interference?
Yes.
When waves in phase meet, you get a larger wave.
That's
That's the principle of stationary waves.
that question.
Right? So watch this here.
Yeah.
Let's say we have let's say I produce a wave here.
Slow motion.
See the wave moving? Right? Y'all see the wave moving here?
Yes, sir.
Right? Look at the wave moving. When the wave hit the wall, right? When the wave hits the wall, what will happen? It will reflect. Right? It will reflect. Right? Watch here. Watch here. Hey. Watch here. Right? And look at what happening. Right? Look at the wave. Just now. Watch here. See the black. Look at the amplitude of it. Look at the amplitude of each one, right? Look at the amplitude. I want you to observe what's going to happen when the blue wave intersects in phase with the red. Right? Remember that blue line is the amplitude, right?
Yeah.
Oh, nah, I remember. Dimensions.
Right. Look at that there. You recognize what happened?
Yes, sir.
Yeah,
You see how
Yes, sir.
you see how the red and the blue in phase?
Yes,
And you get this large wave,
like that.
right? So this is perfectly in phase. But remember, as it moves along, it have all the other phases in between, right?
Yeah.
Right? So you will get smaller and smaller until it reaches what? Until it reaches 0, right?
Yeah.
Let's see if we can get 0.
Yeah, I did.
Ready?
So-
Say your action time slow.
No,
Oh, no.
Right? Okay, what's that? Right? Notice, notice
I read or so I killed that.
nothing.
That's true.
You're saying that? Right. I want you to notice that you have points of antinodes and nodes, right? Antinodes is nothing happening. And then you will see nodes. Right? Sorry, I said the wrong thing. Nodes is nothing happening. Antinodes, max displacement. You're seeing that?
Yeah.
And notice that the stationary wave oscillating, and might be perfect here, because they're not perfectly in phase, but they're oscillating between these 2 points here.
Plus B.
Everybody okay with that? A little higher than that, right? So what's the wave oscillating between there? That wave that you produce is called a standard wave. Everybody okay with that? Everybody okay? Right? And oh gosh, I'm missing.
It is 100%.
Right. That's basically the stationary wave, the max being produced wave. Right? You have 1, 2, 3 cycles in this one. Right? But what's going to happen? Do you all notice? That's my wait, not Josh. Right? What you will notice is that both ends are fixed. This end here is fixed. This end here is fixed. Right? So it's like 2 ends fixed, it's like a rope and both ends fixed. So you always have nodes there. Suppose I open up one end. Which is here. Let me play it up.
So that's why I keep like stretching the.
Just be flat.
Right.
I'm not.
Right?
Yeah, I get it.
One end free. Watch this here.
So you just keep going until it
Like I can pull off.
So you just keep going until it like stretch out.
No, what will happen is I don't know how to speed it up.
Yeah, but I'm gonna.
Right? What you will notice now, Olia, is that you're not going to have node and node anymore. You're going to have node and what? Antinode. Right? What would happen if both ends open? Antinode, start with the antinode, finish with the antinode. Right? So it's important. See that there? See how the end of antinodes? Because the ends are open, no nodes again. Right?
No, I pick one thing is what's the play.
Yes, sir. So stop it.
I'll check the flow update.
Right? Last one. But you see, you'll ever blow into a bottle and hear a loud sound?
Yeah.
That loud sound is the stationary or the resonant sound. Right? If you blow into a bottle at the right frequency and you see a loud sound, right? That is your resonance. So what's here? Last thing on you. Last thing. One end.
So that's like a fiber cube. That's like a fiber cube. That's on the
Right, but here. One end open. What are you getting here? Antinode. Closed. Node. You're okay with that? Alright. And if I adjust the length, things will change, right? Alright. Alright, so let's jump into some stationary wave, small calculations, and we're done.
Here, boy. Here, some partner na.
That's what I
Pais. I love it.
No, you don't kill me. I'll think of you. Already playing on thing too long. I'm not drunk too.
Right. So watch here. So I'm gonna give you the 3 examples of stationary waves, right? Right. Watch here, right?
Yes, sir.
So whenever we have, and you'll see how the form, right?
Yes, sir.
Whenever we have 2 fixed points, right? What you will observe might be a little hard to observe there on that particular one, right? You have different types of waves that are going to be formed. The first one, sometimes we call it your first harmonic. Right? Then you have second harmonic and third harmonic, and right? All those waves look a little bit different. But whenever the ends are fixed, you always have a node. Okay? So I want you to remember this. Picture this wave here. Right? Here is a node, here is a node, 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 node. We have all these nodes. All right? So consider your first harmonic. Your first harmonic has a node here and a node here. And what's in the middle? Antinode. How will a harmonic look? How will that look?
So,
Node, antinode, node. That's okay? And the way you draw a stationary wave, you will see people draw a path underneath here. That indicates that the stationary wave in between here. And we saw that in our example. Right? So some people draw it like this, right? And it's good to draw it like this because the stationary wave could be anywhere between here and here. That's okay? So now this is your first harmonic, right? So how much of a wave is this? Half a wave, right? This is half a wave. Okay with that? Now, when will the second harmonic, how will the second harmonic look? Remember? Right? Remember, harmonic means right? Harmonic means that we have to have a node here and a node here, right? How it will look now? Right? It will have an antinode, a node in the middle, and a antinode again. Same space, right, Keisha? So the second time you see this is this. And it looks like that. The third time you see it, it will look like what? Oh, sorry, how much of a wave is this? Like one wave, right? So I'll just put 2 lambda on 2. That's okay? That is 2 half a wavelength of a whole, right?
I think by the 3 was the
How will the third harmonic look? Adam, how will the third harmonic look? Huh?
That's literally what I just said. I don't know what so.
You went, where you going back
I
again?
went so. I went so. I look so.
He went 4, he didn't go 3.
No, I look so.
Didn't do that.
You gotta get glasses from.
Node. How much of a wave is this?
3.
3 lambda and 2. What you all notice how we going down the road?
I'm not button. It's lambda. Yeah, I love
Right.
City coefficient from non-missing.
So you would recognize that they all increasing by lambda and 2. Right? So every time you hear that loud sound, so for example, if you're going in Russell, right? And if you hear any loud sound, right? Every time you hear a loud sound, right? That means that the wave that's in there is an increase by lambda and 2. Okay? So what will be the next one? Right here, Victoria. You're okay with that? That is if both ends are fixed. What would happen if one end is open?
Yes.
What would happen if one end open?
It's start from here.
So what I know.
Right. So let's draw the first one. Let's draw the first one.
So we start from the X. Yeah.
So it'll be antinode going down to node. Antinode going down to node, right? It will be here to here. Right, Ahmed? How much of a wave is this, Ahmed? How much of a wave is this? Quarter of a wave. So Ahmed, based on what you learned there, how will the next one look? This is first harmonic again. Huh?
And then so.
I don't know what's going.
I see you good.
What the next X?
Oh, stop.
Yeah, sit down.
It's correct. Why is wrong, Oliver?
Because it start from anti-nude.
You should always start us out.
We're doing my tennis. Hey, you do that. You put the X here.
What it two X? It must be the same width, right? I don't know. Yeah. Right. So remember, one end open. Hey. You can't drop one now.
What's it? It's just.
You're starting at a anti-node.
And then you're going so and then you turn out the bus.
What you here?
Yeah.
Right, what you here? You start at a finish at a node, right? And they all increasing by what?
Oh,
By a half. So if you start here, where you finishing now? Right. So in that same space.
yeah.
Better. How much else weave is this?
3, 2, 5.
Right? You'll recognize again it's increased by lambda 2. You'll see that?
Yeah.
And you can figure out the last one, right? Here until
Yes, sir.
here. Right? But please remember to draw your wave like this, right? Right. Who wants to draw the last one? Both ends open. Right? Draw the first harmonic from her. And then draw the second.
Wait.
Both ends open.
So the both ends open. Let's go from node to node. So
Node to node or anti-node?
thing. So
Oh.
Right here. Picture it here. Show me your first anti-node
These
here.
are anti-node.
And show me your next anti-node.
So-
right? Also. Anti-node boy. Right?
I feel so
Anti-node to anti-node, right?
right.
Dot the next one. Dot the reflection of this. Right. Anti-node to anti-node. But
Right.
E and E. E and E.
Where?
Where's
Ah.
how much our wave is this?
Half.
So right lambda on 2. And then do this one.
What's this one? Second. This is this is from here to here, correct?
Same space, right?
I know that just with
Say.
touch with it all.
Right? Well, okay with that? Right? So it's important to understand what the waves look like and the size of the wave. Most important thing of all of this here. Once you could draw the first one, you're good to go. Right? Because you know all the others increasing by lambda and 2. Right? So what I mean fast now. So what I mean fast, and let's turn them into some calculations now.
Good, she would. I think I have to figure it.
Just one or two amida.
Yeah, you did. But this, yeah. I get this now with books. Like when I went to buy these books, they was giving it away. Nah. This one metallic and this that one.
See that again. See that
This
again.
one real bad though. This one. Scrap. Oh.
See what is the bus here?
Don't put it.
Yeah,
See what? See that. The shoes on. So that.
Yeah, I need to.
Now sit down.
Now I.
Yeah, you're on. Oh, you see your ball one? Bro,
That's it. Say only monkey. Wow.
Some there, some
You only monkey?
No, I don't make up with more.
See, we have a monkey too.
He never did
Nah.
Yes. Nah.
But I don't have company store it.
So that's my zest. See, ready for parents? Parents. So it's not parents.
We're not parents here.
Be good.
But when it's palm tree. Yeah, no parents there last year. Had no form to parent.
No, have it next. Very have
They had no form to parent for that.
They'll have it next. And yeah, pick something up.
Oh, yeah.
Let's see, just talking to all the girls and up.
All the kills and ups.
Yeah.
Right, like it's.
Said I'm on the behind my book.
Say, you don't, that's why, yes. Deve ser o enviado, ele jones.
Right, so I want you to put this together. Right?
So you made that ninja stuff.
No, it's a student.
Yeah, they gave a joke.
Anything on TikTok? What is it?
Yes. Should I get up?
So where did one come from? Like big one thing.
A child take pencils. Push it up.
So the word places
Huh?
the word or something.
He gets suspended after he doesn't ask for after
Benjamin Anton.
no.
That's something he leaves school and coming.
Benjamin, come in.
Benjamin Anton.
So I will go soon.
Hey, make your sense. Taste Boy.
When John is my cousin.
Shit, it's a nice step.
Step, yeah, step cousin.
Step cousin.
He's married.
Or some pumpkin type some pumpkin by
Go ahead, my cousin. He's married, somebody with a chat.
Yeah.
I take it out.
We get.
And I go, we got him answer.
just pretty crazy.
So talking.
So we do question.
John, look at actually. I'm not in the images. And they just make sense.
You know, Moscow.
I'll try something here now.
Yeah, let's see. What?
You see that?
That's the next go to minus. Now we going there.
Figure two. You see that? I when it finish up. Right out.
Same, 5. I'm going back.
Oh, no, stop it now.
Yeah, but so. Stop and unsee. You got you. No, I'm good. Take my pen to text proof. You have to make this stop that. Yeah. So, what makes sense?
So what's up?
Now what? Don't almost very places. Doing what?
I want to have that stuff for on.
On the yellow, take the hair down.
What's that? That's all for you.
Go get it, yellow, take the hair.
So I see the real hand.
Now, what do you
Nah, like I'm about to say show up and so much.
And it was a pencil one.
Okay, you missed.
Alright, you ready?
Sit times up.
Project that.
And then you get.
Say you almost get it.
Ah, you know, you know.
I said 5.
And then that's. Oh, it is like. What is sticking? What is going to do so?
I don't.
Yo.
I usually thought you much sorry now.
Yeah, boy.
I got much just not very well.
That's a Spider-Man. So, they did something.
We're not necessarily.
Which was it?
Anyway, we are work with that, right? So figure two shows a stationary. Are you joined, sir?
Yeah.
Like those who not can taste that work out now.
Like 200 or 100.
I think it's 12 on. Go get 12 on.
Yeah, it's
Yeah, it's 240.
Huh?
Yeah, it's 240. No, wait.
That's not what you're saying.
Nice. Like 6,000. Yeah. Like, oh, this one. Like, yeah. My point. That's 6,000. But I think this I think it's useful. You know, like, man, some people, the reasons people, yeah, they don't feel it. Oh, it will help with like my
It's 21,000.
Ah, one N open. One N open. Right? T-shirt. What you got? Nathan, I mean, it's a nice, yeah. So the frequency is 1200 hertz.
Right, 12.
Yeah.
You see that?
And the length of the string, is 0.4 meters. Right? Right. So how many waves you have there?
Two.
Two waves, right?
Yeah.
So lambda is how much?
21,000.
Lambda is, right? Lambda is 0.2, right? Half of this.
Yeah. Oh, no.
Two waves, right?
Yes, sir.
You're seeing that? So speed of the wave is what? V is equal to what? F lambda. F is 1200 by 0.2. How much is that?
Oh, sorry, I didn't want to go.
That's it, huh? That's it.
240 meters per second, right?
So we have the just our presentation. So you see, I had that same 4 meters that wire, right? Now we have like this.
Yeah,
What if I change it like that?
Yeah, wavelength can actually how you stretch it or how you compress it.
Wavelength is already like a measurement, like a
Just need like
symbol in a way.
How the length?
Yeah.
It's just like a one shot on one. Yes.
But if you are jumping something like that, you have to choose might give a small wavelength. Are you okay with that? Let's do our next one now.
Yeah, okay. That's not so bad now. Oh, yeah. Oh, fine. So I want it.
No, give me a shot. Right?
Okay, so. Yeah, so what if you take it? Well, I could take it to fire. So that thing I want to. Oh.
Nothing much.
Yeah, again, true.
Yes. No, just wait. Money so walk on it over. Scary boy.
This one, yeah, we'll go like the messenger again, and I say, so you know, let's try to get this better. Who's that? I say,
That's all. Yeah, forget it.
Select color, you go on.
anything of the fire. Why want to use it?
Oh, it's good.
I say we got more mark and avoid doing one house. Hold on, now I find this one.
Write down something for Ramanujan now. And can one more liquor matter?
Yeah.
Enemy.
But I think we got number 9.
Paul. Which Paul?
So I think long.
No, bravo.
Jesus. Maybe I'm Paul Holland.
No. Let's imagine it, didn't
And even like that,
Your son.
right?
Ah, okay.
Yeah.
Right, just one question. This,
Which is Brandon.
what is the answer here? I mean, what is the answer here? What's the answer here, Olivia? Which one will have the greatest amplitude? What?
No, D.
So
I'll see the driver. Are you sure?
Yeah.
So it should have the same amp, it should have the same length.
B.
Right, so the answer is B. Alright, try part C here and we got. Try that then. That's it, I say I sit down, oh, we'll call this someone else, stand up it. The one on top, the one on top. We do one on top, okay. Oh yeah, so we try the one on top quick.
I
I think that's speed on the film.
We think go back.
Alright, so. What's that here, try thing now? Last one and we done, we're going home after this. Alright, guide eyes there along there. Guide eyes there. You write down the frequency,
And the length is between 0.5 and 1.8.
right? And then the speed of sound is that.
And the speed of sound is 300.
One end open, right? One end closed, one end open, right?
Right, sir.
Calculate the lengths at which you hear resonance.
Yeah, find the
L,
So actually two different values. So like
think about what you want to get. Remember I gave you a diagram here? First one is observe at what? One end open. Nathan. For one end open. When is the first harmonic observed? Right, how much of a wave is that? Quarter of a wave. So the first one is heard at a quarter of a wave, right? Do you know what a quarter of a wave? No, I mean like in question. But you had to find first then. A quarter of a wave, right? So you had to find the wavelength first. This is we can find the wavelength there is to say.
Lambda is equal to E.
Is that correct? We can for him that 340 over
40 over 280. 34 times.
no, give me decimal, that's he need decimal. Right, so first harmonic happens when? First harmonic happens when? Huh? Am I going to finish it? First harmonic happens when?
I see.
Right? So first harmonic happens at how much of a wave? quarter of a wave, right? Do me a favor, find a quarter of this.
So it's 0.30225.
0.30, 0.30225.
0.3025.
Right. Is this in between there?
No.
Will you hear it?
No.
So when is the next one heard?
2 3/4.
3/4. So find 3/4 now.
Yeah. Let's say 9.07. 9.07.
How much?
1.03. I don't know.
You see the idea? Fido. Come in. I'll press it on my phone. Go now, press it on my phone. How much is this? Right? Will you hear that? Yeah?
Yeah.
Nice. Well, when you hear it again.
2 5 and 4. So we're up.
And we keep adding half pi.
Oh shit, so we want to
It will be 5 pi and 4. How much is that?
5 1 point.
How much is that?
6 hours.
Would you hear it?
Yes.
Would you hear it? Do one more and see if you will hear it out.
Not serious.
Good that. No.
Right? Last one.
2.11.
So the last one was 7 pi and 4, right?
7 not 5.
Sorry, 7 lambda and 4.
Yeah.
How much?
2.11.
So would you hear it? Nah. So you're only hearing it here. Only at these two. So you're only going to hear the second and the third harmonic. That's okay? Alright, all done. Right, take a little break.